Have you ever, opened an old wooden cupboard, maybe at your grandmother's house? Or unboxed those heavy winter coats after a long summer?
Oh, yes.
And you get hit by that very distinct sharp smell. It's almost pungent, right?
It's a smell you never forget. It's the smell of mothballs.
Exactly. And if you've ever looked at the packet of those mothballs, or even some air fresheners, you might have seen a chemical name that's a bit of a tongue twister.
The chlorobenzene.
Or paradichlorobenzene, yes.
And chemically speaking, that smell is the smell of a halorene.
And that leads us perfectly into our topic for today. Welcome back to the deep dive. Today we're opening up Unit 6 of Class 12 Chemistry.
Halogenes and halorenes.
That's the one. But we're not trying to, memorize the whole unit in one go. We're zooming in, specifically on the preparation of halorenes.
And this is a very, very critical topic. For any Class 12 student, this is often where organic chemistry starts to feel a bit tricky. But if you get this right, the rest of the unit becomes much, much smoother.
So we have a stack of goats here. Textbook concepts, reaction mechanisms, some exam tips. Our mission today is to understand exactly how we attach a halogen to a benzene ring.
And more importantly, why it's not as simple as just mixing them together.
Right. Before we jump into the mechanism, let's just quickly unpack why we should care. I mean, apart from making mothballs, why does a student need to master this?
Well, there are three main reasons, actually. First, from an exam perspective, this is a trap. The method for making halorenes is fundamentally different from making haloalkanes.
So you can't just apply the same logic.
Absolutely not. If you try using SN1 or SN2 logic here, you will lose marks. Simple as that.
Okay.
Second, practically speaking, these compounds are essential. They're what we call intermediates, used to synthesize major pharmaceuticals like aspirin derivatives and many agrochemicals.
So they're building blocks.
Exactly. And third, if you understand this preparation, you will understand why halorenes are so resistant to other reactions later on. It really sets the foundation.
Okay, so it's the key to everything that follows. Let's get into the core idea then. If you had to give me the zero-level explanation, the simply possible way to describe it, what would it be?
Okay. At the simplest level, halorenes are prepared by a process called electrophilic aromatic substitution.
Electrophilic aromatic substitution.
Electrophilic aromatic substitution. Okay, that sounds a bit heavy. Can we break that down?
We can. Basically, it just means a halogen replaces a hydrogen directly on the benzene ring. But, and this is the most important part, it absolutely requires a halogen carrier.
A halogen carrier.
It's a catalyst, something like iron 3, the bromide February 3.
Okay, so let me get this straight. I can't just take benzene, mix it with, say, chlorine, and just hope for a reaction.
No. If you just mix benzene and chlorine, nothing will happen. You can wait forever. The reaction needs that catalyst to even start.
I want to help our listeners visualize this. For everyone listening, maybe close your eyes for a second, unless you're driving, of course. What should we be picturing? Okay, imagine a benzene ring. You know that shape? The perfect hexagon with a circle inside representing that cloud of electrons.
Got it.
Now, you want to attach a halogen, let's say a bromine atom, to one of the corners of that hexagon.
Okay, I see the ring and I see the bromine just sort of waiting outside.
Right. Now, in simpler compounds, haloalkanes, you might just use UV light to get things moving.
Yeah.
But here, that won't work. The benzene ring is very, very stable. So you have to imagine using a catalyst, that February 3, to activate the halogen.
Activate. When you say activate, what's really happening to the particles there?
So think about the charges. The benzene ring is electron-rich. It has all those pi electrons, so it acts like a nucleophile.
It likes positive charges.
It's attracted to positive charges, yes. But an ordinary bromine molecule, Br2, is neutral. The ring is not interested in it at all.
It's like trying to introduce two people who have nothing in common.
That's a great way to put it.
Mm-hmm.
So the catalyst comes in. The February 3 is a Lewis acid, meaning it's electron hungry. It grabs onto the bromine molecule and pulls electron density away from it.
Ah, okay.
This makes one of the bromine atoms positive. It becomes an electrophile. Now that it has a positive charge, the electron-rich benzene ring is suddenly very interested.
So the ring sees that positive charge and it attacks.
Yes. The ring's electron cloud reaches out and grabs that positive bromine. The ring opens up temporarily. But to restore its stability, its aromaticity, it has to do something.
What's that?
It kicks out a hydrogen atom.
That's a fascinating dance. So if we need a solid, insert-safe definition for the board exam, what should a student write down?
Okay, for the exam, you should write this. Halorenes are prepared by electrophilic aromatic substitution, where a halogen, activated by a Lewis acid catalyst like February 3, replaces a hydrogen on the benzene ring, and the reaction preserves the aromatic character through rearomatization.
Got it. Catalyst activates halogen. Halogen replaces hydrogen. Aromaticity is saved. Now, you said earlier that this is a trap for students. What is the biggest misunderstanding trigger here?
Ah, the biggest mistake is trying to apply the rules of haloalkanes to benzene. So many students think, oh, I made a haloalkane using free radical substitution with UV light, so I'll just do the same for benzene.
It seems logical if you haven't studied the mechanism properly.
It does, but it's completely wrong. See, free radical methods do not work on the benzene ring itself. If you use UV light and chlorine on, say, toluene, the chlorine won't attack the ring.
Where does it go?
It attacks the side chain, the methyl group attached to the ring. To get the halogen on the ring, you must use electrophilic aromatic substitution with that catalyst.
That is such a crucial distinction. Light hits the side chain, catalyst hits the ring.
Precisely.
Okay, to make this concept really stick, let's use some analogies. You know I love a good analogy. How should we think about this catalyst's role?
Let's use the gatekeeper analogy. Think of the benzene ring as an exclusive VIP club. It has a high wall around it. That's its protective aromatic structure. It's a very secure place.
The benzene club.
Yeah.
I like it.
Right. Now, the halogen molecules, like Cl2 or Br2, they are visitors trying to get in, but they don't have the right credentials. They're just ordinary, not activated enough for this club.
They're just standing at the door getting ignored by the bouncer.
Exactly. Then comes the catalyst, February 3. The catalyst is the gatekeeper's credential machine. It takes the visitor, the halogen, and it stamps a credential on it. It turns that neutral halogen into an electrophile.
Which is like giving it a VIP badge.
Yes. Now that the halogen is an electrophile, a legitimate visitor with a badge, the security allows it to enter.
So it goes in.
It goes in, displaces a hydrogen who is already inside, and takes its spot.
And the hydrogen gets kicked out of the club.
Unfortunately for the hydrogen, yes. But
Yeah.
the club stays exclusive and stable.
I like that one. There's another I've heard too, the lock and key.
Yes, that's a good alternative. Benzene is like a high-security lock. An ordinary halogen molecule is a blank key. It doesn't fit. You can try, but the lock won't open.
And the catalyst is?
The catalyst is the key-cutting machine. It shapes the halogen into exactly the right form, an activated electrophile. So it fits the lock perfectly and opens it.
Okay, that makes sense. But tell me, why does this concept even exist? Why did chemists have to figure this out?
Well, it solves a huge problem.
Yeah.
How do you attach something to a benzene ring when the ring is so stable it resists reacting?
Right.
Without this catalytic method, we literally could not synthesize key drugs or polymers. We wouldn't have certain flame retardants or specific antibiotics. We needed a way to breach that stability without destroying the whole molecule.
It's amazing that a simple powder like iron bromide is the key to all that. Okay, I want to go back to the mental movie. We had the club, but let's try one more visualization.
Okay, let's try the hexagonal fortress.
I'm listening.
Picture the benzene ring as a fortress, shaped like a hexagon. At each of the 6 corners, there's a sentry, a guard. These are the hydrogen atoms.
Okay, 6 sentries guarding the fortress.
Now, along comes a bromine molecule, Br2. But on its own, it's weak. It can't breach the walls. But then, the catalyst, February 3, arrives. It acts like a weaponsmith. It activates the bromine.
How so?
It turns it into a warrior, Br plus K.
So the catalyst arms the bromine.
Yes. Now you have this warrior, Br plus K. It attacks the fortress. The wall of the fortress opens temporarily, just for a split second. The warrior rushes in.
And what happens to the guard?
One of the hydrogen sentries is displaced. He has to leave his post. The warrior takes his place. And then snap. The fortress seals itself back up. It re-aromatizes.
So the fortress is intact again, but now one of the guards has been replaced by a warrior.
Exactly. And that restoration of the fortress wall, the re-aromatization, is the most important part.
That's a very clear picture. So we've got the theory. What does this actually look like in a lab? If I'm running this reaction, what am I seeing?
Okay, let's take the bromination of benzene. You start with benzene, colorless liquid. You add bromine, Br2. Now, bromine has a very distinct, deep red-brown color.
Okay, so colorless liquid plus a red-brown liquid.
Now, if you just mix them without a catalyst, nothing happens. The red-brown color just stays there, it's telling you I haven't reacted.
Right.
But the moment you add the catalyst, some iron filings or Fibriona 3, you see a change. That red-brown color starts to fade.
And the fading means the bromine is being used up in the reaction.
Correct. It's reacting with the benzene. And you'll also notice acidic fumes being released. That's HBr gas. That's our sentry leaving the fortress.
So the fading color is the visual proof that the catalyst is doing its job.
Precisely. Without the catalyst, that color would never, ever fade.
Now, earlier we talked about mothballs. That's a technology application, right?
Yes, beta-chlorobenzene, the
Hey.
classic example, used in moth repellents and also in making PDC. To make it, industries chlorinate an existing molecule, chlorobenzene,
And the catalyst matters there too.
hugely. The catalyst and the conditions control something we call regioselectivity.
Big word. What does it mean?
It just means controlling where the second chlorine goes. We want it to go to the pair position directly opposite the first chlorine. That isomer is more valuable, it has a higher melting point, it packs better into crystals.
So it's not just about making the reaction happen, it's about making it happen in the right spot.
Exactly. Structure dictates property.
This is where it gets really interesting for me. The counterintuitive example you mentioned, the idea that free radicals don't work. Can we drill down on that? Because I feel like students would think, radicals are super reactive, surely they can attack benzene.
It's a very common assumption. You think, hey, free radicals attack alkanes, benzene has C and H, so why not? But actually, free radical halogenation of benzene usually results in a mess.
A mess how?
You might get polyhaloalkanes, or more likely, the radicals will attack the benzylic position. That's the carbon attached to the ring, not the ring itself.
But why? Why does the ring reject the radical?
Because radicals look for weak bonds to break. And the CH bonds directly on the aromatic ring are incredibly strong because of the ring's stability.
I see.
A radical just doesn't have the energy profile to break those bonds cleanly. But if there's a side chain, like a methyl group, those CH bonds are weaker. So the radical takes the path of least resistance.
So to attack the ring, you need the catalyst.
You absolutely need the catalyst method we discussed.
That is such a key distinction. Radicals for the side chain, catalysts for the ring.
That is a perfect summary.
Okay, we are getting towards the end of our dive here. I want to make sure everyone is ready for their exams. Let's do our exam-safe clarity lines. What are the absolute must-know takeaways?
Right, let's nail this down. Here are the keys to scoring full marks on this topic. Number 1, catalyst requirement.
Okay.
Haloarene synthesis absolutely requires a Lewis acid catalyst like Febr3 or LCl3. If you write the reaction without the catalyst, it is wrong. No catalyst, no reaction.
Got it. No catalyst, no marks.
Number 2, mechanism type. This is electrophilic aromatic substitution, or EAS. Do not confuse it with free radical substitution or nucleophilic substitution. The words matter.
EAS.
Number 3, preservation of aromaticity. Remember the fortress. The ring temporarily loses aromaticity when the halogen attacks, but it must restore it by losing a hydrogen. The final product is aromatic.
The fortress has to be resealed.
Exactly. Number 4, regioselectivity. If you're adding a second halogen, its position isn't random. Halogens are orthopara-directing. You get specific products.
It's not luck, it's chemistry.
And finally, number 5, and this links to the next topic in your unit, resistance to substitution. Once you've made a haloarene, that carbon-halogen bond is very strong. It's resistant to being replaced by nucleophiles.
So no simple SN2 reactions on a haloarene.
Don't even try it in an exam paper. It won't work.
That is a golden list. So to wrap this all up, let's do a quick summary.
Let's do it.
We learned today that haloarenes are made via electrophilic aromatic substitution. It's a mouthful, but it's the only way.
All right.
We use the analogy of the gatekeeper. The benzene is the VIP club, the halogen is the visitor, and the catalyst is the gatekeeper with the VIP badge.
And don't forget the hexagonal fortress. The catalyst arms the warrior to breach the wall.
And we visualize the lab experiment, that red-brown color of bromine fading only when the catalyst is added.
That visual proof is key.
And finally, the golden rule. Never forget the Lewis acid catalyst Febr3. Without it, the reaction simply fails.
That is the single most important takeaway from all of this.
So, as you head back to your textbooks, remember, mastering this catalyst concept is the key to unlocking aromatic chemistry. Once you understand how to get that halogen on the ring, you're ready for everything that happens next.
Absolutely. It's the gateway to the rest of organic synthesis.
Thanks for diving in with us today. Keep asking questions, keep visualizing those molecules, and we'll catch you on the next deep dive.
Happy studying.